In last video, we talked about the ideas for the quadratic discriminative analysis. And in this lecture, we're gonna introduce another very popular classifier based on the normal distribution. It's called the linear discriminant analysis. Okay, it's called, the short abbreviation is LDA. LDA. So LDA is a variant of the QDA. Okay, LDA is a subclass. Is a subclass of classifier of QDA. Remember when we in what sense it has so the assumptions for the assumption for LDA is each class not only will assume further the variants are same. Do you remember in previous case that we assume each class they have their own variances. So, for example, here when we derive this QD minus QC minus QD, we assume they have different variances. Where is that part? Yeah, in the quadratic discriminant analysis, we assume each class have different variances. For example, this class and this class, they have this. I guess this variance is bigger than this one, right? Little bit bigger than this one. But in the linear discriminant analysis, we further assume we have further restriction that each class has the same variance. So we have less. We have further assumptions. So QC x minus QDX, the decision function can be further simplified. This will equals to, remember this QC in our previous one, we have this, right? We have this one. Okay, so now let's rewrite this part. So we have negative x minus mu c square divided by 2. Before we have the QC, sigma c, right? But now we just assume they have the common sigma. So we don't have label c here. Minus d times natural log sigma c plus the log of the prior probability in C class. And then we minus, this is the QC function, right? We minus QD function. So we have the 2 sigma square x minus QD square minus d natural log sigma d plus natural log the prior probability in this D's class. Actually, and this simplifies to, so here we assume they have same variance for each class, so we don't have separate notations for the variances. So this cancel out this. And then we have negative 2 sigma square x minus mu c square minus x minus mu d square plus the differences among the two prior distribution Okay, and this can be further simplified to I will use some show some calculation here. So x minus mu can be written as this is square, right? So this can be further written as x squared minus 2x dot product with mu plus mu square. Okay, by apply this formula to both equations, we're gonna have negative 2 sigma square, and we have the x. The first term has x squared, second term has x squared cancel x squared. So we have, after you simplify, we get mu c minus mu d dot product with x. We have two term here, right? So 2 cancel this 2, so we don't have 2 here. So, and we also have negative term here. So negative get to positive. So we don't have negative here. Minus the length of the mu c minus mu d square over 2 sigma square plus natural log pi c minus natural log pi d. Okay. So actually this is a linear decision function, right? This is a linear decision function. Linear decision function. So in other words, this part is our w, right? And the whole thing behind this is our alpha. It's our alpha. Okay. So we have a linear decision function, and we have the linear decision boundary. So we have decision boundary. And the posterior probability linear decision boundary will just equals to the h is just equals to the set of the x, such that omega times x dot product with x plus alpha equals to 0. And the posterior is the probability, the y choosing the class C given the x is just equals to sigmoid function or logistic function transformation of this decision function. X plus alpha. Okay, so in other words, for example, so here we can give some examples here. So this is a posterior probability. So this gives us a posterior probability. Okay. And we have two Gaussian distributions, right? We have two Gaussian distributions with equal variance now. we have the equivalence but different locations. So you can think this is a mu d. You can think this is a mu c. And as we go from the smaller value to the bigger value in x, at this here, this gives us a decision boundary. This is a decision boundary is just a point in one-dimensional case. If we have only one feature, this is our decision boundary. And on the decision boundary, we have the 50% chance to be in class D or class C. And for the 2D case, we have two normal distribution. One is located here, one is located here. So the probability, the posterior probability to pick C is, you give this is the probabilities, okay? You can think this is the one feature, x1, and this is another feature, x2. Okay, and this will also gives us the linear decision boundaries. So if we have the multiple categorical case, multi-class. For example, we want to classify the digits. We can use a LDA. But this now the decision boundary is a straight line because this is the linear decision boundary. Linear decision function. Okay, so there is a special case too. Special case. When pi c equals to pi d equals to half. Suppose in prior we know 50% the population will be classified to C, 50% of the class will be classified to D. And our decision function, you can think this, so this disappears, right? This part cross out. Okay, so we only have the first two parts. First two parts, and the decision function is the Rx, it just equals to mu c minus mu d dot product with x. Okay, so that's the first term here. You let this equal to 0. We don't have this part constant. We let it equal to 0. So the sigma square does not matter anymore because we can multiply sigma square to both sides. So you let this equal to 0, right? You multiply sigma square to both sides, you get this decision boundary. Decision boundary will equals to this plus half mu c minus mu d. This is square divided by 2. So I will rewrite it one more step. You're gonna see what's this decision function. Plus, so because this is square, we can rewrite this as mu c minus mu d multiply dot product mu c plus mu d divided by 2. Okay, actually this is a decision function, or this is a decision boundary. Do you see what's this decision boundary? This is a decision boundary where we pick the, for example, we have the two data points, two cluster points, right? And we have another class of the points. So this tells us, this decision function tells us we connect the center and the center point, right? Center point. So anyone remember what's this is the classifier? This is actually the centroid classifier. centroid. Which we introduced in the first or second lecture. Okay, I think that's about the LDA. So this is LDA. So I'll continue in next video.